Okay, ladies and gentlemen, this is section 7-4. This is recording number 1. So what we've been doing is talking about confidence intervals, and we've been doing this for the mean. We had 2 sections for that, and we did it for proportions. Now we're going to talk about confidence intervals for the variances. And of course, if you know the variance, you know the standard deviation. Okay, so let me go to that section, 7-4. And the author discusses here about why do we need to know this? Why is standard deviation of a variable, why is it sometimes just as important as the mean? A common example that we use is quality control in a factory. We want to make sure that all the parts are going to fit together. So we may have the average size, but we want to know what the variability is. So we want to be able to estimate that. And in order to estimate that, we have to use the techniques that are in section 7.4. Okay, so it turns out that we're going to use this new distribution. It's called a chi-square distribution, and I'm going to discuss that in a little bit of detail in a few moments. The author basically just says, hey, this is it. This is what we use, the chi-square family of curves. Now, this chi-square family of curves, as the name implies, it is a family of curves. Depends upon the degree of freedom, what it looks like. So remember, the degree of freedom is 1 less than the sample size. So if, for example, you had a sample size of 16, the degree of freedom would be 15. And you can see that as the degree of freedom gets larger, it starts to get more symmetric. It looks more and more like a normal Gaussian type curve. And so you can see that for yourself. Okay. Oh, here it says right here, at 100 degrees of freedom, the chi-square distribution becomes somewhat symmetric. Okay. All right, so I'll let you read all this. The key thing for you is to understand is that we're going to use the chi-square distribution in order to come up with the same kinds of estimates that we've been doing in the previous sections. The coefficient, this chi-square coefficient that we get from the table is what we're going to use to multiply times the appropriate basically the appropriate measure of dispersion. So give me a minute here, and we'll see how that works. All right. So to start with, this is what the author is saying: is listen, you've got to use these values for the chi-square distribution from the table. Now, previously, we had the t distribution and the z distribution. Both of them were symmetric. So for convenience, what we would do is we would only find one variable. We didn't have to find, I'm sorry, maybe I shouldn't say variable. Maybe I should say coefficient. We only had to find one of these values, one of these critical values, because the z distribution is symmetric. So if you have one, you can have the other. We cannot do that with the chi-square distribution because it is not symmetric. So this is a generic sketch of the chi-square distribution. And as you can see, it's not symmetric. So here's what we're going to do here. And let me get that table. Okay, it's table G in the back of your book. Now, it's very difficult for me to bounce back and forth from the textbook to this table. It's almost impossible. What you're going to have to do, in my opinion, is as you're watching this video, get your textbook out, have this table G there so you can kind of bounce back and forth. I think it'll be a lot more clear that way. It's just too hard for me to bounce back and forth. So let me close this. All right, so here we go. Here's the way to handle this table. Okay, the left column denotes the degrees of freedom. Okay, gosh, I should have pointed that out. See, degrees of freedom. You see that? Okay. The various values that are in the table tell us what the area of the curve is to the right of that particular critical value. Okay, so for example, let's see here. If we have degree of freedom of, let's say, 10, and we wanted the area to the right of, we wanted to find this critical value here of, let's say, 12, let me use this one here, 11.071. So 11.071, the curve, the family of curves is a family of curves. So the curve that we have for a degree of freedom of 5, if I wanted the critical value, they gave me 0.05 to the right of that critical value. What would I choose? I'd choose this critical value, 11.071. Boom, right there. So 11.071 to the right of that critical value, that area there, that alpha area there is 0.05. So that's, in a nutshell, that's how you use this table. So let's see if we can look at the textbook examples. Okay. Now he kind of goes in circles here a little bit. The title of the book is a step-by-step approach. So he's always very, very algorithmic. He always has, okay, do this, do this, do this. That's just not the way my brain works. I just don't think that you're going to be able to memorize that. So I think it's better to understand the concepts, and then you can kind of follow your nose, so to speak, and just do the problem. Okay. So for example here, let's take a look. Find the values for chi-squared right, chi-squared left for a 90% confidence interval when n is 25. Okay, so if n is 25, the degree of freedom is 24. Okay, chi-squared right, that's this guy right here. We want the 90% confidence interval. So just like we've done before, if it's a 90% confidence interval, that means that we have a 10% error budget. We can make a mistake 10% of the time, but sometimes we'll make the mistake over here and sometimes we'll make the mistake over here. You have to split it up. So it's not alpha, it's alpha divided by 2. It's half of alpha. So if we're talking about a 90% confidence level, alpha is 10%, half of alpha is 5%. So what we want then is we want the appropriate critical value that gives me 0.05 over here on the right hand side. So that part should be straightforward, right? That part shouldn't be any problem whatsoever. Let's take a look. Get back to the, give me 1 second here. Okay, so it's 0.05, or otherwise known as 5%, is half of the error budget. So I want this area over here of 0.05. So I'm looking for this column right here. Here's the column I'm interested in, and it's n that was given to me is 25. Therefore, the degree of freedom is 24. So my row is right here, 24. So it's row 24, alpha of 0.05. So if I had 2 fingers on the screen, I'd do a lot easier here. Right there, 36.415 is what I claim it should be. Okay, and I'm happy to say that I am correct. For an alpha over 2, half of the error budget of being 5%, degree of freedom of being 24, that's the critical value. That's the guy that I plug the number value in here. To the right is going to be the 5%. Okay, now there's only one table. So, we don't have a separate table to do the area to the left. Okay, it would make our lives a lot easier if we did, but that's just not the way they do it. What they do is they say, well, this table is strictly the area to the right. So I want this area here, the colored section here, to be 5%. So if the colored section here is 5%, that means the area to the right, all the way to the right, everything to the right, that's going to be, this is 5%, so this is 95%. And it is so that my column is going to be right here, the 95%. My row is going to be the same degree of freedom as before. That's 13.848. So 24 is my column, and I want 0.95. Is that it right there? screen, it's not that great a resolution. I think that's it. 0.95 is are the columns. 0.95 is a column. The row is 24, so 13.848. Okay, and that's what I get. So this first example that you must do, do what I just did. You must work it out, draw your little cartoons, make sure you understand, put in all the extra steps, make sure you understand this, because you must be able to figure out what's my chi-squared left and what's my chi-squared right in this cartoon. Okay? Because if you don't understand that, you're not going to understand the next steps. Okay? So here's another cartoon that he's doing here. 36.415. That critical value gives me 5% over here. 13.848 gives me 95% to the right. Therefore, it gives me 5% to the left. That's exactly what I wanted. Those are my two critical values that I'm looking for. Okay. I'm not sure he calls them critical values at this stage. I think he uses that term later on for something else, but that's what it is. It's just, these are critical values. These are boundary values. These are values that, if you're to the right, you get a certain area. And on this one, if you're to the right, you get a certain area. If you're to the left, you get a certain area. Okay. So just so hopefully, I hope I'm not beating a dead horse here, but do you understand that this value right here, call it a critical value or a boundary point. For this boundary point right here, 5% of the area is to the right, 95% of the area is to the left. Similarly, over here, for this boundary point, 95% of the area under the curve is to the right, and 5% of the area under the curve is to the left. Okay, so you must be familiar with this concept in order for this stuff to make sense. Okay, and he talks here about what do you do if you don't have the degree of freedom in the table. What do you do? It's just very straightforward. I'll let you read that. Okay, so now this is the proof of the pudding right here. Just like before, we had the concept of what does our population mean? What is our population P? Now we're going to talk about what is our population sigma squared. What is our population variance? Here's the formula. Now, doesn't that look horrible? But it's not. I swear it is not. Okay. So this is sigma squared. This is the variance. So this is the standard deviation. You just take the square root of everything, right? Okay. All right. So make sure you read this. Okay. S squared is a symbol for sample variance. S is a symbol for sample standard deviation. So pay attention. If the problem gives you sample deviation, S, you got to square it in order to put it into this formula. So here's the formula. Okay. And again, I don't ask you to memorize these. You'll have access to these formulas. If it's well, of course, I think the exam is going to be a take-home exam. But if you were in the classroom, you would have access to the formulas. I'd give you a formula pamphlet. Okay, so where does this come from? The book does not derive it, but I will for you, just real quick. Okay, so here's some assumptions. The key thing here is population must be normally distributed. If the population is not normally distributed, it does not work. Okay. And here's a rounding rule. That obviously is something that you do need to know, but I'm not going to read it to you. You guys can figure that out by now by yourself. Okay. So let me end this recording, and then on the next recording, I'm going to explain where this came from, and then we'll start doing a couple of the examples here.